Okay, tonight I'm going to be starting to talk about drives and control of motion, and it's chapter 17. But I'm going to start talking about it from experientially and some of the things that has happened. And I want you to understand that in a roundabout way, I'm talking about chapter 17, but I'm talking about it outside of the chapter first, and we're going to work our way into the actual working of the chapter. So basically, this is a chapter on motion control, and that would be without robotics. We're not going to include robotics, okay, but we're going to talk about all kinds of controlling of motion, okay? Right? So that's the main topic. And I want to go through some examples tonight with you and get you to think in terms of how to look at motion control as a subject, and then maybe we can start picking away at the actual chapter itself. But I have several examples from real world examples that I want to share with you before we get into it. So back in the late 70s, Owens Corning Fiberglass got a contract with I don't know if it was the Saudi Arabia government or whoever it was, to build 128 acres of fiberglass Teflon coated fiberglass fabric. And there's 120 acres that was being built as basically a tent near the airport in Mecca, Saudi Arabia. So that was the goal, was to coat 120 acres of fiberglass fabric with Teflon. Okay? In order to do that, they had a plant in Ashton, Rhode Island that did the coating, that they were planning on doing the coating, but they had one line that they had built, and then they built a second line, and neither of these two lines were able to successfully coat the fabric, the first three coats. It took 7 coats, and the first 3 coats were critical that they be put on and not stretch the fabric. After the 3rd coat, the 4th, 5th, 6th, and 7th coat didn't matter because there was enough Teflon. It was like a rubbery substance in the fabric, and it would give and it wouldn't stretch after that. But the first 3 coats, if it stretched the fabric too much, it would destroy the integrity of the fabric. So the first 3 coats were the complicated coats, and we built 2 oven lines, and neither one of those lines was able to do that. And I want to show you the process. And you say, well, how did you ever get this done? Well, there was a competitor that did it, and I don't know how he did it. It doesn't really matter how he did it, but he did it. And they also built that company. I don't know who it was, but that company also did the Pontiac Silverdome. So prior to the 120-acre tent in Jeddah, Saudi Arabia, there had been another project where they had built a Teflon-coated fiberglass in plant or a fabric to use for the Pontiac Silverdome. If you know about the Pontiac Silverdome, it was used. I don't know exactly when it was built, but it was used for the football stadium for the Lions until they built Ford Field, and then they tore it down. So it's gone. But it was a facility much like the facilities around here for sports complexes, where they blow up like a balloon the roof, and that they built the side walls, but then the roof was all with fiber. It was fiber, and it was glass fiber, a woven glass fiber, and that's how that was done. So anyway, I'll explain to you what I knew about this second line, and I was the electrical engineer in charge of not of the construction, not of the design of the oven, but of the overall electrical controls for the oven. I was the electrical engineer in charge from Owens Corning Fiberglass. Okay, but they bought a turnkey project from a company, and they were supposed to make it so that it would work, and it never worked. But I'm going to show you the problems that basically we had. Okay, so this is a line where you have a roll of fiber. It was woven. It'd be like carpeting, and they took this and they ran it through pull rolls, and then they put it on a conveyor, and then they took it and they ran it into a dip tank, so it went underneath, and in here was where the Teflon was. And then they took it and they went up an oven and over a roll and down a roll, and then they come back down here. They had another roll here. Now they may have had rolls in here. I don't know. I don't remember for sure. I don't remember all the pieces, but this was 3 stories tall. This would be like the first story, the second story, and the third story. So this was pretty, maybe 20, 25 feet tall, this oven was. So this was in an oven, and they let the fiber go in and out of the oven, but basically this was heated. I don't know how hot it was, maybe 300, maybe 400 degrees. It wasn't super hot, but it was hot. So it was a heated area, and then it took the moisture out, and then it came out, and then it was rolled up again. So you basically went over here, over some rolls, went through some pinch rolls, and then you rolled it up. All right, somewhere in here, everybody, if you pull a loose woven fabric too tight, it sometimes can stretch beyond what it destroys the fabric, and that's what happened. So in this number of motors, there was enough pull and push that it stretched the fiber too much, and it destroyed the integrity of the fiber. So they ran a number of times and it never could get to work. But this was a failure, okay? So again, not that everything that I've been involved in was a failure, but this one was not my design. But I spent a lot of time working on trying to figure out if the guy that was selling this was selling a good product. He put sensors in at a lot of locations that had LVDTs that would actually monitor the force on the material as it was going by that point. In other words, there would be they would have like a dancer roll that would go up and down. That would actually monitor if there was it would be like, here would be one roller and here would be another one. And if the product started to go like that, this would be rolling on that, and it would have an angle. And if that angle, like a pot, this would be a pot. And if this started to go down, it would speed this up a little bit. They had those a lot, okay? So they basically had feedback at every place they could, feeding every motor that they could, and it still didn't work. And again, not all systems are going to work. You're going to design some systems that kind of work, some systems that work well, and some systems that don't work well. And this one, for whatever it was worth, never worked well. Okay? This is called a dancer. It kind of goes up and down, and that's a dancer roll, called a dancer roll. All right? So the purpose of this is to not let it get too high. You don't want to get it taut, but you want to your goal is to have it just a little bit of drag, just a little bit, not by much, but just a little bit. And that would be ideal. All right, so that was one example. Now, I have another one that I did fail on, and I was the person that didn't get it to work. And this is another example of now, those motors were all DC motors, by the way. Those are all DC drives. This is going to be one with a servo motor. And basically what it was a grinder that was a massive thing with a motor on it. The motor's here, and there's a grinding wheel like this on it, and it goes up and down, and then this axis right here is on a servo motor. So basically you had a worm gear that took it up and down, okay? It went up and down. And then you have a part right here that you would place here, and then this would come down and grind the face of that, and then just take this a little bit of metal off, and then go back up. And this was a trying to take a Olivetti drive contraption, and it was they took that and they were trying to put that with a Modicon controller, trying to mesh the two together. And I didn't realize it, but the brake came off of this, and it slowly went down, and it came down, and it hit, and it broke the piece. And they said it could never be replaced; it could never work again. And I didn't cry, but I didn't get asked back ever again to that application, or never asked back to that plant. So that was a fault of mine. But that was a single axis motion control, where you're controlling to 1,000th of an inch. Okay, you come down, and then this is a spinning device that you're spinning with an AC motor, but this up and down was to control to 1,000th of an inch, where you actually control very tight tolerances. And that was a grinder. Okay, and that would be an automotive grinding application. I also had several examples of work where I did work personally with replacing of one type of motor with another type of motor. Okay, so this was 20, 25 years ago. The majority of these were being done, but there were large DC motors that were being replaced as drive motors for various lines with inverters. And every one of these applications had to have some kind of an interface between what had been the controls for this guy and what were the controls for this guy. For a while we used relays, and then we eventually used a small programmable controller to actually control the interface between the two. Okay? Now I did a number of these applications with one company, and they all worked. So it's not like I can't make things work. These all worked, and they were replacing these with these, and we had a good run with all those. So that was another application. So again, not that everything works or everything doesn't work, but I'm giving you some examples of real world applications. Also, not a lot of applications that I've been involved with involved single axis motion control. So you have to basically work at this and get this to work prior to doing your startups, because if you are involved in a startup and it involves motion control, that motion control application should be pretty well proven and working before you start your startup, because if you don't, you'll be standing there for months working on starting up a motor. And the reason for that is most of these applications, the number of variables is huge. If you think the PID is a hard thing to set up, the motor applications are a lot worse, because you have all the variables in the motor itself, and then you have the variables in your program, and that it's phenomenal amount of work to get all that to work. Okay, that's my observations from this. Another observation from motion control is this: it's a very fragmented market. It is a lot of specialty applications. So there's, under motion control, it's a very fragmented, and you can find special applications that do a lot of the things that you might want to do. Special application programs, not necessarily in a PLC. These can be in a PC, these can be in a other computer system, but special applications dominate the motion control industry. You can find it's a very splintered, very splintered market. So a lot of this, not all of it, but some of it has been taken over by robotics. So if you can, many of them have been solved with a robot, but not all of them. Some of them you cannot solve with a robot. So you're faced here with some people have done stuff that you don't know how they did it, but they did it, and you basically buy it from them. Other people work with robots, and they try to do stuff with robots that may be better done with multi-action coordinated axes or single action, single control ones. I don't. How do I get this back? It is a very fragmented market. I'll be blunt. It's not one that is. How do I get this back? So when you're making decisions, and you probably won't be the one making decisions for a while, you will be the one who will actually have to implement it. You can take like a FANUC system, FANUC CNC system, and program it. You can take a FANUC robot and program it. You can also take a PLC and program it. And this is what I'm going to be talking about, okay? But to get motion and to control motion, there's all different types of ways of doing it. And I'm going to talk a little bit now about the Rubik's Cube project. Okay? It's a project that uses motion, and it uses it to basically turn the robot. And I'm going to show you that motion now. So this is kind of what we have as far as the Rubik's Cube project. Okay, so here's this. I just wanted to show you that the black one is a 7, which is basically a line to fill in. So on this screen as well, I wanted to show you that you can spin with the array called the spin. We'll talk about that later. But as you do your code programming of your spinning of an axis, and that's the one that's to fill in. So basically, you're committed to doing something. So if I wanted to go 6, 5, 4, 3, 2, 1, and then I start here. 1, 2. I'm going to go to another one. Sorry about that. 6. I would then see. Week 9. This is a better one. Sorry about the blast. So here's the move relative. Then we execute the rest. Now, what are these? It's only turned 90 degrees. Go in a negative direction. One is under the watch table. So now you click on it. It shows you. Hopefully it turns. Maybe we will get lucky this time. Son of it turn 180 degrees and do that step. So that gives you a little bit of an idea as to what you're going to have to do. You're just going to say, but I have to do it for every position to do every row. Well, what we do is after it does, and click on it, show it to you. Hopefully it turns. Maybe we will get lucky this time. of it, 190 degrees, and then do that step. So that gives you a little bit of an idea as to what you're going to have. And you're just going to say, but I have to be in every position to do every level. Well, I think what we will do with that call, you probably get kind of, you'll be able to find things. But for right now, the answer is good. Back to the 8's better. Sorry about that. I'll get back. We'll get it back. And it does say that. See, it says 6, 5, 4, 3, 2, 1. And that 7 is the one that's the black one, and that's the one that's the next one I wanted to fill in. So basically now you're committed to doing something. So if I wanted to go 6, 5, 4, 3, 2, 1, and then I start here, 1, 2, 3, 4, 5, 6, I would then see that array from 0 through your last start being able to solve the program in the background. You can look at the watch table, or you can look at various parts of the program and see it. And when you're online with the glasses on, you can see the various things going on. Now, I'm pretty click this to on, but when you first see it, you have to click this button right here to turn on, and then you click reset, and then you move through the motor using this switch right here. This would be give you the white, the green, and the red. Now this is a relatively numbers already here for it is 100, and I'm going to click the. I'm going to show you the picture of that. I'll get that picture over there to that and see if I can see it. Let's see if I can see it right now. It's kind of small, but maybe I can see if I can get it down there, see if you can actually see it. In fact, I'm going to increase the size a little bit so you can see that on the screen as we're going through this. Okay, so we're going to go back. We're going to try to see if we can get this to run now. Let's put the red one and see if it moves, see if it runs. See the axis moving? Now, in that piece, you add a little bit, add like 1.5 instead of 100 to that, and do it again. It'll come back. Now, back into the figures. It's a little sticky in times, so you might have to do that to get started. Okay, see that? Let's go to the next one. The green. You see that? You see it controlling the axis? Blue first. See, these are just 90 degrees. And I'm going to select the yellow at the bottom. And then the orange. Okay, now we need to do something different. Well, let's go back to the white. Okay, so that gets you a little bit of an idea about the axes moving. So basically, what you have is you have a command in your program controller that basically takes and gives a command to a motor to do something, and that's what this chapter is about. This is a chapter on motion control, and the Siemens program controller has the ability to control steppers and servo motors, little servo motors and stepper motors, it can control them. And it also has the capability of looking at pulse counts coming into it and being able to count exactly how many are coming in per unit of time. So it has a high-speed pulse count input. It has the ability to drive a servo motor out or a stepper motor out, and those are all functions that they built into that little block, that little box, that they didn't have to, but they did. So that gives us the advantage of, in that little PLC, of doing some very sophisticated things that we would have to pay a lot more money for otherwise. And that's why we use the Siemens PLCs on this project. The Allen Bradley will program just as easily as the Siemens, but because of those discrete inputs and outputs that we can use to do some very that do some very specific things that we usually couldn't do with a PLC. That's why we're using this one. And they kind of made it like an Arduino almost. They made it just a little bit like an Arduino that would give you the capabilities of doing some of these specialty things. And that's their prerogative. All it took was to add another layer of controls on a chip outside of the basic chip that did the basic PLC work. So they added a little bit, and in order to do that, you have a little bit extra control, but it gives you a lot more flexibility, and that's why they're very popular, and that's why people are using them to an extent, is because they have these specialty I/O capabilities. And I don't want to overemphasize it, but I do want to say that that's why they're being used. So it's a block that you turn on, and like I said before, after chapter 14, we call these the big box instructions. And the motion control instructions and the PID instructions are case in point of that kind of capability. So there are other instructions that are special instructions, but these are special instructions that just basically control a single axis or multi-axis of a system. Now I want to start talking about some of the systems, and I'm going to jump over some of this stuff, but I'm going to talk about some of the systems that you can get into. And this is from a book from ABB, Asaya Brown Boveri, and they pictured several processes that some of them need feedback control and coordination, and others do not. So some of these you have to have multi-axis coordination, and that is within a millisecond usually. So you're talking about sub 1 millisecond coordination of axes, and some of these you do need that, and some of these you don't. And some of them, depending on how you define the process, you can flip from one to the other. So for instance, this application right here, they define, and I wrote this part, they had the picture and I basically wrote the definition of it. But basically, if you have boxes that are coming in at varying lengths of spacing between them, and your only desire is to have at least, like say 4 inches or 5 inches between the boxes, that's relatively easy. But if you say it must be exactly 5 inches in between the boxes, that is not as easy. Because when you move a box between two conveyors, you have to match the speeds exactly. They have to be matched. You can't get away with having one speed and the other at another speed. Why? Because you don't know when the friction of the one overtakes the friction of the other. You don't know that. You can assume that but it doesn't always work. You can get skewing of boxes, you can get all kinds of stuff. So you cannot assume that. But you don't need that if all you're trying to do is to get at least 4 or 5 inches between boxes. But if you say, I have to have exactly 5 inches between boxes, that's a totally different animal. And that's what this is about here. So if you're looking at applications, you have to be very specific as to what you're actually asking for. This is an application with a motor here, a motor here, and a motor here, okay? And each of those motors either have to be matched or you have to figure out what your definition of what you need is. Now, if you have, say, at least 5 inches and that's it, that's a different, you might have to have the matching of the speeds, but if you say they have to be exactly 5 inches between or 4 inches between, then you have to definitely match the speeds, okay? If you don't match speeds in general between one conveyor and another, if you have a product that can be scratched, it will get scratched, all right? Because one of them will rub, the other one it'll follow the one, but it'll rub on the other one. So again, that's the kind of thing that you have to think about when you're doing this. So again, this is something that you could control with a programmable controller, and you would have control of this motor, and this motor, and they would all have to be working based on these criteria down here. Any questions about that? Now you get into the idea of relative versus absolute motion. All right? An application like this, you never go back to home. You have to ask the question, am I ever going to go back to a home position? And as long as you're rolling in one direction, the answer is no. So if there is no home position, then it is relative. If there is a home, then you are absolute. And before you can run an absolute, you have to declare a home. So in other words, you'll see that with an absolute, you have to initiate a home position, or it won't work. If you say go to position 0, it goes back to that position that you declared as home back whenever. So if you had a home position for something like this, and you said let's run it for an hour in one direction, and you say go back to home, it would run an hour in the opposite direction and go back to the original position it was when you first started. You don't want that. Very rare if you do, but you can if you want to, but that's very rare, especially with conveyors. Okay? So now you're beginning to get the idea that this has to do with conveyors, it has to do with matching of speeds, it has logic. This is logic as well as, this is all the above. And how do you control that? And how do you make this work? Okay? Now, I'll be blunt. I don't do this a lot well. And I'm not scared of it, but you have to be very careful when you define these systems how accurate it must be. In other words, if you have a system like this and you say, I have to have a blank that is cut that is exactly 5 inches long or 10 inches long or whatever, all of a sudden this becomes a coordinated system. What do I mean by coordinated? It means that the speed of the motor running the pinch roll and the speed of the motor running the cutter have to be synchronized. If you picture a cam, when a cam comes around, it clicks and does something, that would be a synchronization, okay, like a cam. But cams do where? These do not. So this is a system that automatically looks and has feedback control, and then it absolutely right on a button it does its job. So that's coordinated axes. So you have to ask the question, are we talking about coordinated axes, or do we care? Can we live with a quarter of an inch one way or the other? If we can, probably we can get away with non-coordinated axes. Now, the newer brand of the Siemens, the 1500, the 1200 Siemens, the little guy has coordinated axis control in that little box. So the little box that you're talking about, that you're looking at, the 1500s, the 1200, excuse me, the 1200, the 1215, the 1215 DC, 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 now has, Rev B has coordinated control. So it can be used in that environment. The older ones can't. The older ones did not have that capability. So they knew that they needed that to get some extra job opportunities. They had to put that in, and they did. So they saw them being used for a lot of applications, but they wanted them used for more, so they put that capability in. That means that the feedback between one axis and another axis has to be checked less than 1 millisecond apart so that you can actually respond and control the activity. This is another one just like this one. You have to ask the question, what's my accuracy? What do I have to cut to? Do I have to cut to a tenth of an inch, a hundredth of an inch, a thousandth of an inch? All of a sudden you have to ask, what's my speed of my line? What's my accuracy? How accurate do I have to be? And if it has to be dead on, maybe a 10,000th of an inch, oh, for sure you've got to use coordinated axes. Okay? It depends on the speed and the accuracy. Here, not. I cannot foresee you ever using coordinated axes here. Why? You're trying to hit something with something else that is big enough that you can hit that hole without having to worry about a quarter of an inch. Okay? I've asked this question. You wonder, what is he ever going to ask on a test about this stuff? I've asked this question to write the program for this actual application on test before. Will I this time? I don't know. But this is where this is at. Okay? I don't want to scare you, but I have. Right? So how would you do that? Well, you would see the limit switch. You would see it drop off the limit switch. Then you would move it so much further down the road, and then you would stop the box. Then you would see the front leading edge of the hat. Then you would march the hat over the edge, and then you would hope to hit the box. Okay? Now, how would you speed that application up? You'd move them both at the same time, wouldn't you? And that's where it gets fun. Because that's what you have to do. Real world, you can't you can't move slow. You have to move multiple things at the same time. So the faster you can move the hat after you position the box, if you can get it close to being ready to go over the edge by the time the box is in position, you win. So this is a cycle time issue more than anything else. I wouldn't want to write this program. I would not want to write this program. This is a tough program to write if you want to get right down to it. What do you have to do when you're writing a program like this? Well, you have to do a bunch of configuration before you set it. When you're setting this thing up, you have to do a configuration page. And you have to do this. You have to basically do what they call the lampshade part of it. You have to declare an acceleration rate. You have to declare a terminal velocity, and you have to declare a deceleration rate. This is your XL rate, your decel rate. And this is your terminal velocity. You have to declare all those. Those can be dynamic, or they can be fixed, but you have to figure them out. So again, in applications like this, you have to declare all this stuff in order to get it to work, and they all have to work. If you want to make the Rubik's Cube go faster, what do? Check up the velocity. Would I ever change the XL and the decel? Probably not. That's why you have overshoots. And with a system like that with no feedback, how do you know if you overshot? You don't. So basically, you're running a stepper motor with open loop, and it does not know if it went over 5% or 10% or whatever. So you basically have to slow your accelerate and your decelerate down to the point where you may have to run like this. Flatter accel and a flatter decelerate. So you don't miss them. So you don't miss your endpoints. See where the fun starts? It ain't fun, but there's a lot of parts and pieces to actually configuring this guy right here. A lot. And that's what I was trying to do when the thing came down and crashed on that grinder. I lost the enable bit. The magic enable. If you hit an enable on a servo, you hear it humming. Okay, the enable bit. In a servo, it hums. In a stepper, what does it do? If your enable is on, what happens? It holds position. It won't let it move until you tell it to move, and then it'll move. So basically, it stiffens it up. It acts like a brake. And you'll hear it with a servo. It hums. Physically, you can hear it. But it's called the enable bit. And until you get it enabled, you should have the brake on. If it's a gravity fed thing, you should have the brake on. The enable didn't come on my application. The brake turned off, and the thing came down and it cracked. Easy peasy. Not. It's not easy peasy. Anyway, here's the application that I grew up on. This is the application that I saw when I was first at LOF, and it wasn't with plywood. It was with glass, and it wasn't with a saw. It was with a scribe. But it's the same exact application. You have an encoder, and then you read how far you want the piece to be, how big a piece you want it, and then you send this across at an angle, and it then cuts a perpendicular line to the side of the piece of glass. Okay, so this was a continuum of glass, and then they would run a scribe across, and then that would be that piece. Now, what about this has to be accurate? There can be no waviness in it. It has to be perpendicular to the side. In other words, when you're cutting that piece of glass, here's your piece of glass. It has to be right on, and it has to be straight. It can't be curved at all. How curved can it be? A 32nd of an inch. Okay? So you can vary by a 32nd of an inch, and that's it. A little trivia point from the different companies of glass companies. Guardian Glass cuts a 32nd short. LOF cuts right on. So if you order a 2-foot long piece of glass, LOFs will be right on. Guardians will be a 32nd of an inch short. Why is that? You're putting it into a frame. And if you put something into a frame and it's the exact size or a little bit big, what happens? It won't work. If it's a little bit small, what happens? It's just a little loose, and the grouting or whatever is around the edge will hold it. So basically, they're getting what? Every 200, 300 pieces, they're getting a free piece of glass. You say, well, why doesn't everybody adopt that philosophy? I don't know. Now, that may have changed with the new owners or newer owners with LOF glass. But with the old LOF glass, if you wanted a 2-foot piece, you got a 2-foot piece. You didn't get 1 foot 11 inches, or you got 2 feet. You didn't get 1 foot 11 inches and 30 seconds. You did not get that. You got exact piece. Okay, but this is a coordinated axis. Now, when they bought this system from Reliance Electric, they bought it with 4 cross-scoring axes, 4 cross scores. Or how much do you think in $1972 or $1973? I told you how much the computer costs is $100,000. How much do you think the controls for this cost. In $1973, $250,000. And in the 80s and the 90s, they were still doing the same thing, and they were still buying them from Reliance Electric. It's a lot of money. What would that be in today's money? Well, I started at Libby Owens Ford for $900 a month. So what is the price now of an engineer going out the door? What is it? How much do you think you'll make a month today? I was making 900. I'm figuring dollar for dollar, so I was making 900 a month. That's $10,800 a year. What are you making now as you go out the door? What's the hoped on salary for most of you? 80? 85? 75? So you would say, what would be the price of this today? Approximately 7 to 8 times that. It would be what? It would be about $4 million. Is that right? If you were to buy the same thing today? Do you know what you can do this for today? The price of a 1215 DC processor, which costs you all of what? About $400. If you know how to program it. If you could program it, you could actually make it and do it for about $400. The processor would be about $400. That would cost to make that happen. I'm not saying that anybody is going out today and making that application, selling that application using a 1215 DC processor, but I'm telling you it could be done. Why? Because it has a capable algorithm in it that is a block that does that function, and it will do multi-axis control, and it will do that. Now, I'm not absolutely sure how they will do that today, but I know that that's what they put into the newer processors. If you go in and you look at the new, when you configure on version 20, if you look at the version 20 software, they have a Rev B or a B processor. That one of the changes from the A processor to the B processor was this function. And they can do coordinated axes, and I don't know how many, but they can do coordinated axes. All right, that's one of the functions they put in. So again, I'm not trying to impress you, but I'm telling you that this can be done, and it can be done for a lot less money than they did back in the day. Now, they may still be doing this, oh, we have to spend $1 million to do this, or $500,000 to do this, or whatever. I don't know what they're spending, and I don't care what they're spending. It doesn't matter to me. But I'm just saying that could you do this for $400 today? And the answer is probably not for $400, but for probably $4,000, you probably could. Anybody doubt that? With a good PLC, and the Siemens people do have those PLCs, and Allen Bradley does too, you could probably do this for about 4K in that range. So you've just basically destroyed this market. Coordinated axes can do things like this. What else can you do with the coordinated axis system? How many of you are in the robotics club? Anybody here in the robotics club? Nobody in the robotics club in here. Anybody know anything about the robotics club? Have you seen the people in the robotics club doing their thing with all that kind of good stuff? Do you know what they do? What's the main thing that they do in the robotics club? They shoot off rockets, but what else do they do? They build a tube that has a outside to it that is fiber, right? They build a machine that actually does that, right? Does anybody know about any of this stuff? Has anybody heard about what they did with that fiber making machine that they have? I think I know what I'm talking about. I'm not absolutely sure, but I think I know what I'm talking about. This is a fiber making machine that basically attacks. Okay, so if you have a form, and then you wrap fiber around it, with glue, what have you got? You take the form out, you got the shell of a rocket or a shell of whatever. Now, what else can they do with this? You can make a gasoline storage tank or for filling stations. You can make storage tanks for all kinds of stuff. Put an end on them, capped in, and then you're in business, okay? Now, what do they have to do that? Here's the side of you have to rotate a drum, right? This is a drum, and you have a rotating piece. What do you have to do to make this work? You have to change the angle of this, and the angle is a fixed angle that then what do you want out of this? You want to lay these pieces, and it's not just a fiber, it's a group of fibers. So you have a bunch of fibers like this that becomes like a tape, and you lay the next one right over the last one. All right. So what's your purpose here? All right. So if you look at this microscopically, you're laying one fiber, and then you're laying the next fiber just right like that, right? So that they just overlay just a little bit. So there's no gaps. There can be no gaps. Why? If there's a gap, that is a weakness, and that becomes a leak in your rocket, that becomes a leak in your gas tank. You can't have that leak. You have to guarantee that they overlap. But you don't want them to overlap too much. Why? Because you're paying for this tape. So you want to make it just a little bit, but not too much. You want to do this again and again and again. Okay, and they are at an angle. And that angle has to be what? The angle that is best suited for this product. So you lay it like this, and then you lay up, you keep doing it, and then what? It looks like this at the end. Okay? They're crosshatched. What does that give you? Your maximum strength. Okay? How do you do that? The coordinated axis. This axis has to be coordinated with the axis that moves the piece across. It has to be coordinated. It cannot be just let it rip. You can't do that. It's the same way if you want to machine a screw. Okay? You want to put threads on a screw? When you do that, you have to go back and you have to hit it exactly at the right spot, or it won't. If you're threading a big screw, you're actually machining out metal. So you have to come back and you have to hit it exactly the right spot, and then you machine it out. And you have to keep doing that until you get the threads out. So it has to be coordinated axes. Point is, they each have to know where the other one is, and there is a tolerance on that, and it has to be. The faster you make it, the tolerance goes way down. It has to be sub 1 millisecond. So the two axes have to be talking, and they have to be communicating back and forth so that they're in agreement to a tolerance every millisecond. That's fast. But that's what's being expected. That's what's been expected for the last 30 years. So you can't get away from it. You have to do it. Okay? Here, you might not be exactly that way, but you have to be fairly accurate. Here, you have to be pretty accurate. Why? Because you have to be straight, and you have to be within a 32nd of an inch. And that depends. What does that depend on? It depends on the speed of the glass. And by the way, they put a thermocouple on how do you get the speed of the glass is a basic question. The speed of the glass is a roll, a rubber wheel riding on the glass upstream. And they put a thermocouple on that roller. Why do they do that? Because the diameter of the roller can shrink or expand based on the temperature in the room. Enough that it can throw you off. So they basically read the temperature in the room, and they augment or they change the speed based on that temperature. So again, where is good enough? That gives you an example of it ain't good enough unless you've got everything covered, and that's one of the last things that I would ever think of to cover. But that's how they get that accuracy. They put a thermocouple on the roller to make sure that the temperature, if the temperature changes, like it does around here, that wheel diameter will be compensated for by that thermocouple. Ugh. Does everybody get the idea that this is not an easy? This is where everything kind of coalesced. This is one of those example problems that you don't just go into and say, I'll do that in half an hour. I'll get that taken care of in half an hour. By the way, I was looking at some of your applications of the three pumps, and I don't know. I kind of close my eyes and give you your 4 points, and we go on. I wish I had the time to go through and analyze every one of those programs, but I don't. But I wish that I had a way of filming, looking over your shoulder about how that one's done, because I don't believe some of them are going to do it. But again, I can't prove that, and I just accept it and go on, and that's life. But I do want you to know that that's one that I'm a little doubtful at times, but I don't know. So again, I'm not trying to belittle it. I'm just saying that's a tough problem. The reason that I say that is because nobody's come up to me and said, boy, that was a tough problem. It took my breath away when I did that problem. Now, I may be old, but I expected that a little bit. Boy, that was a tough one. I didn't get any grins from anybody this time around. Maybe I just missed them. But if you do that one well and do that right, you'll spend a lot of time on it, and it is not easy. That being said, it's okay. I understand. You're trying to get your 4 points, get on with life. I'm not picking on anybody in particular. I'm just saying, I wish somebody would have come up to me and said, that was a hard one, and given me the, but it's okay. It's all right. It is a hard problem, by the way. So these are all hard problems. In this chapter 17, they're all hard. They're none of them easy, all right? You look at every one of these and you say, what is he talking about? That can't be that hard. They are. They're very difficult to do the first time. Once you get them down and once somebody solves the problem, then it's easy. But until they solve the problem, it is not easy. Everybody follow that? There are some really tough problems. And they get into the physical side, they get into the programming side, they get into the electrical side. They're all three involved in some of these applications. By the way, I don't want to keep you too long, but I want to tell you a story about the application of this guy at Laurinburg. When the first time that they put one of these things in, they had an absolute encoder on the device here. So this device that went across. Okay, so here's your line, and here's the so it goes across like this. It travels like this. Okay, as you're moving, it goes across. So they had an absolute encoder on the end of this thing so that they know where it was at, and there were 12 bits in that absolute encoder. Now, an absolute encoder gives you an exact position of the wheel of the 360 degrees at any instant in time, and it was a 12-bit guy, and it was very accurate, and they did a very good job of it. But those 12 bits came back to the program controller, or back to the computer, and the way that they wired it was they did this. Each of the bits went to the bit next to it, okay? And that's the way they wired it. So they were cutting glass at, I, I don't know the exact temperature, at the exact, not temperature, but the exact speed, about I don't remember, but it was 300 feet per minute or 300 feet, no. It was at regular speed, and then they went to high speed, okay? Now, they measure speed in thickness of glass, and 0.2 inch and above is regular speed, okay? They went to 0.09, they call it 90 thousandths, and that was 90 thousandths, and this is a higher speed, okay? So they went from here, 0.2, 0.25, that's a quarter of an inch thick glass, that's 2/10 of an inch thick glass. They went to really thin glass, and all of a sudden, not every time this thing went across, but occasionally when it went across, it would go out about halfway and then come back and wouldn't make a full cut. What was going on? They didn't know. They called everybody in and asked everybody, now, do you know what's going on? Do you have any idea what's going on? And everybody did this. Nobody had any clue what it was about. Now, they had run for about 3 months. They had been running for about 3 months when they went to this higher speed glass. And they had no idea what was going on. So they called the guy who had designed the system, and his name is Tony Cachet, and he was a smart guy, and he was with Reliance Electric, and he flew in a private plane. They got him a private plane to fly from Toledo, Ohio to Laurinburg, North Carolina. The plane got hit by lightning and had to make an emergency landing in Washington, D.C. So again, everybody was worried about how we were going to get this thing solved, and now the plane was hit by lightning. So everybody thought, this is something else. And then he came in, he was really kind of upset from the mere fact that he had to come and all that kind of stuff, but he did. He came in and he looked around, and basically he went down and looked at the wiring, and he saw this wiring, and he came back and he said a few choice words, and basically at that point in time, everybody kind of looked chagrined and said, uh-oh. So what the wiring was there was a noise between these two wires. This is a twisted pair, unshielded twisted pair of wires. And there was noise leakage at higher speeds. And every once in a while, you had a parity bit that wouldn't match because you're reading on the edge, and sometimes that parity bit would not match if you had a little bit of a delay. This is called RC time constant delays, what it was. So one of them would be delayed just a little bit, and the other one wouldn't be. And it was cross-talking between these wires. So what they had to do was every wire one wire go like this, and the other wire had to go to the ground wire. So the other wire was the ground wire. So this, and then this, and then this, and then this, and then that's how you did it, and that worked. Never again did we have any problem. But that was the problem. Unshielded twisted pair, you cannot use them as pairs. You have to use them as individual wires with the other wires of ground. Easy to see, but the guy took a chance. The guy who was doing this took a chance, and he thought he could get away with it. Saved half the wiring. It was easier to do. You could save half the wiring, and it looked neat and everything, but it just didn't work because of crosstalk between wires. So again, absolute encoders are not used very much anymore. This is one of the reasons, because people were using them wrong. But that was how that played out. So again, it can be anything. Tony Cachet, by the way, is the original designer of what? What is he known for after his days with Reliance Electric? He was the person that actually did the design of control logics, okay? So as you're looking at the Allen Bradley RS Logics 5000, the look and feel of that program is all done by this guy right here. He was the brilliant guy that sat down and wrote the specifications and made control logics, the new programming language for Allen Bradley. He did it, year 2000, but he was the guy that did it. Anyway, beside the point. But in that earlier era, he was the guy that came down and got struck by lightning, his plane did, and then came and told us what we had done wrong. I didn't do that, by the way. That was not my design. I would have not done that. And the guy who did that didn't get punished. He got promoted to chief engineer. So it didn't matter. It wasn't a big deal, but that's neither here nor there. So this is the kind of thing that you're going to get into. Now here, again, you're hitting a box. No big deal. You can be off a quarter of an inch and nobody cares. And by the way, this again is something that you could actually end up doing as a project. Programming that little guy would be an easy programming problem for a second test. I'm setting you up. If you haven't figured it out yet, I'm setting you up for a second test by this kind of stuff. But this is the kind of thing that I've asked this problem before. Whatever. And this one right here, I've asked this one before. Now, this is an easy one, by the way. This is a non-coordinated system because you don't have to have two axes working together. You're only doing one axis at a time. Now, this is something that you would say, why not use a robot for? And the answer is, I probably would today. But why would you not? Why would you not use a robot? If these are very heavy members, and by the time you would buy that robot, you would pay for it 10 different times over. And if this is a long run, in other words, if this is a long way down from here to here, you might find that it'd be more economical to build it as a non-coordinated 3-axis motion control system than putting it into a robot. But this is where you have to ask that question. You're going to make those decisions. I'm not. Okay? But you're going to make decisions like this. Should I use a 3-axis non-coordinated axis motion system? Or do I buy a robot for that? Good question. This is a system called an ASRS. You're putting boxes into storage locations and taking them out again. This is a non-coordinated axis. You don't have to coordinate these axes. You hit a spot, you stop. You don't have to go there coordinated. You just go to a spot and you stop, and then you go in or out, and that's it. But this is non-coordinated axis, but 3 axis of control. It's a very sophisticated system. By the way, we had one of these in 2350 for a while. If you'd have been here 10 years ago, we tore it out about 10 years ago, but it was there until about 10 years ago. But we had one of these systems, and it went all the way to the ceiling in that room. Now, is this a coordinated axis? I don't know. I do not know. It could be. It doesn't have to be. It could be. Maybe hard. Maybe. What about this? Is this a coordinated axis system? Not really. What are you trying to do here? Get the shrink wrap around it, right? Do you have to be within a quarter of an inch? Do you have to be within a tenth of an inch? Do you have to be within a hundredth of an inch to hit the right spot? No. Can you be off a little bit? Yes. Now, where it might need to be coordinated is in what area? The stretch. So you might have to run them at a slightly different speed in order to stretch it just a little bit. Does everybody follow that? You don't want it sagging. You want to stretch it just a little bit. So you're going to let this out. If this is on a brake of some kind or whatever, I don't know if it's on a brake or whatever, but if you had this on a motor, that you would actually control this, the time, how fast this would go out, you might have to make this go a little bit slower than the speed of this. But I doubt it. I don't know. They're going up and down? Nope. Nope. It does not have to be coordinated. By the way, who does this? Who builds these kind of systems? There's a local company that builds these out in Waterville, Ohio. Kaufman. If you've never heard of Kaufman before, they do this kind of work, and they do a lot of it, and they're very successful at it. But they do more than just this. They do the whole system. Everything from where you bag or put your product into a bottle or whatever to getting it into a ready to go out to the forklift driver on a pallet, they do. And I'm not advertising for them, but if you ever look on their website, Kaufman website, you'll see some of the most fantastic automation projects that you won't believe your eyes. It's Kaufman, Kauffman, and they are local, Waterville, and they do hire. I'm not trying to say that you wouldn't want to work for them. You probably somebody in here might, I don't know, but this is what their baseline is. They basically do shrink wrap, but then everything else around it as well, robotics, everything else. But their basic line is shrink wraps. And what is this? This is back to my grinder. This is my reminder that I failed bigly in that job that I did. It was for GM up on Alexis Road. And as a result of that, that was in 1996 I did that, by the way. And as a result, projects that you can do here. Okay? Rubik's Cube is just one example. It's not the only one. But there's 2 or 3 that I can show you. And I will next week, Monday night, we'll go through a couple of examples. But I can give you a couple of really good examples and tell you other programming examples and show you how to program them and all that kind of stuff. But this is the picture that reminds. This is not the way that one looked. This is a manual grinder, but daggone it, it's a grinder. What is it about grinders that is dangerous? This wheel, if it is hit just right, can fracture and break apart and be like a bomb. It can throw pieces, shrapnel all over the place. So you got to be very careful around them. So you got to operate them very carefully, and you got to be nice to your grinder. You don't want to get it all ticked off at you, but there are caveats to it. It can hit a rough spot and fracture and throw shrapnel all over, and people do get hurt. So it's not the most pleasant machine to be around because everybody knows that. So again, you want to be careful around these things because that grinding wheel can and has in the past split apart and made a mess. Okay, so that's all I've got for today. Any questions anybody's got? Any comments? What's he going to ask us on the motion control, right? I have no clue. I just know that after you go through a couple of examples, you'll be able to, if you pay attention, you'll be able to do whatever it takes in order to get through a problem from me. My goal is to warn you, more than anything else, that these are not easy. These are, if there's any area in this whole book that I'm going to warn you about, that if you jump into it, you might end up 3 months later pulling yourself out of the hole. This is one of them. This is not an easy thing. You might spend 2 weeks, 3 weeks, 4 weeks before you even get the axis to move. And you say, why? Because there's 40, 50, 60 variables. There's a potload of variables that you have to get them all right or it won't work. Some of them are easy. Some of them aren't so easy, but they all have to be done in order for you to get them to work. So anyway, I'm just giving you a heads up that in the real world, these are not to be taken lightly, but they can be done, and you should know about them. Okay?